And it gives me great pleasure to have as our first keynote speaker, Professor Holger Hermanns. Holger is a full professor at Saarland University in Saarbrücken in Germany, where he's the chair of dependable systems and software on the Saarland Informatics campus. He has previously held positions at various places in Germany, in the University of Twente in Netherlands, at INRIA in Grenoble, and he's the former dean of the Faculty of Mathematics and Computer Science at Saarland. Those of us in RV know him quite well, but his interests, research interests include modeling and verification of concurrent systems, resource-aware embedded systems, and applications of energy to informatics. And he has been one of the outspoken proponents for proactive algorithmic accountability. He has more than 200 peer-reviewed papers with an H-index of 48 and HA index of 92. And he's in the past co-chaired various prominent conferences in the formal methods community, such as CAF, Concur, TACAS, and KEST. And he has delivered several keynotes at many different conferences. So it's really our it's my great pleasure and our privilege that we have him speaking here. He's also on the steering committee of ETAPS and TACAS, and he's president of Friends of Adblue, one of the most magical places for those of us in computer science. And he's vice president of the ETAPS EV Association. He has received the Dutch Vernieuwingszimpels, sorry if I'm butchering the pronunciation, and the German Preis die Fakultät Tanges Informatik Award. This is my best attempt at pronouncing long German words. And he's an ERC advanced grantee and elected member of Academy of Europea. He holds several national and European research grants. So without further ado, I'm very honored to welcome Holger to this Runtime Verification 2021. And let's see what Holger has to tell us. This is a very interesting topic. Holger has been doing work on this topic for a few years. Those of you who keep tabs on the automotive industry might remember that a certain European car manufacturer was caught trying to do some shady things with respect to their emissions test. And at that time, several of us joked that maybe computational cheating should be one of the new topics that we look at. But Holger actually went out there and his group has formalized what this means. So we have a very exciting keynote talk in store for us. So I should now stop talking and please, let's all welcome Holger.
Now you can hear me? Can you hear me? Good. Yeah. Okay. So thanks a lot. Yeah, well, it's a great pleasure to be with you. I would have loved to, of course, to be in LA. I chose a modest title, namely bringing runtime verification to the masses. And let's see whether I can explain what I mean by that. It is joint work with Bernd Finkbeiner and Maximilian Schwenger from the CISPA Helmholtz Center for Information Security, and also joint work with Sebastian Biewer, Maximilian Köhl, and Yannick Schnitzer, who are in my group. My name is Holger Hermanns, and I am at Saarland University on Saarland Informatics Campus in Saarbrücken, Germany. Okay, so what is this about? Well, I mean, behind this, it was already called, let's say, algorithmic accountability. I have a slightly different take of the things I'm interested in. So the claim that I have, and some others, is that there is an explosion of opportunities for software-driven innovations nowadays. But this explosion of opportunities comes with an implosion of the human opportunities and capabilities to understand and control these innovations. And I could now give a long talk where I detail this in many areas. I don't do that. If you want, we can discuss this. By the way, I have decided you can post questions in the chat during the talk. You can also unmute the mic. Let's do it interactive if you want, or we do it at the end. I decide to be robust. Now, what we have here is what we think is there is a need for what we call perspicuous computing. Now, what is that? Well, there is a center for perspicuous computing now, which is about 2 years old now. Its planned lifetime is 12 years. So we have another 10 years to go. It is funded by the Deutsche Forschungsgemeinschaft. It has in the order of 30 fully funded PhD students and another 20 to 30 that are collaborating. So it's quite a big thing. And well, it has this funny word perspicuous there. Now, what is perspicuous? If you look this up in your favorite search engine, you find something that sounds like it could also be transparent, interpretable, comprehensible, explainable, plausible, but we decided to call it different just because each of these words has already 25 different interpretations in computing and beyond, so that we decided we needed a word that somehow has, we can basically brand the meaning ourselves. And what we mean is really that we want systems where the human can follow what's going on, and let's say also by that, systems that are composed out of that are still, let's say, if you have cascades of these systems and of decisions, they are still, it's still possible to make someone accountable if something goes wrong and so forth. Now we have designed, sorry, I should probably tell you a bit who is actually there. So this is an initiative of people in Saarbrücken and in Dresden. So people that are in the formal methods community. Here is Crystal Bayer, for instance. This is Joël Ouaknin. Bernd Finkbeiner is there. You should probably know. Hupak Majumdar is there. Maria Christakis, you may know. Christoph Weidenbach, maybe. This guy is in AI. This is Jörg Hoffmann. Franz Bader, you may know. And yeah, well, there are also a few others. So this goes out into HCI also quite a bit. And what we are doing there is we are kind of looking at the life cycle of systems, and we distinguish design time, runtime, and also inspection time, with the idea being that if something goes wrong at runtime, you want to understand what this is, and you may want to feed this back into design, right? So there's actually a feedback loop that is meant to happen here, right? So of course, there are different stakeholders in the various phases, and they have different desires with respect to perspicuity. And that could be, for instance, at design time, it could be to understand what you are actually designing. At runtime, to plausibilize to the user what's going on actually. And in inspection time, to justify whether certain behavior was correct or incorrect, right? These are the things that we're looking at. And what I will be discussing with you mostly is something that is at runtime. It's called Lola, Lola drives. It's about plausibility, making things plausible to the user at runtime. And the runtime is the car running on the road. This is what we're going to discuss. And for that, I have to give you a little introduction into what is now like 5 years ago, what has happened. And it is about what is coming out of the exhaust of, let's say, modern cars, actually very modern cars. Well, there are certain gases like CO2, NO2, and CO, and so forth. So, and there are also particles that are coming out there. And well, the question is there any issue with that? Well, so what's bad about especially the NOx quantities that are in the exhaust? And well, there is an answer that is given by the European Union on this. It's quite simple. It kills, and at least it kills statistically speaking, right? And the statistics are like that because of the NOx emissions, there are about 400,000 premature deaths every year, 6.5 million fall sick every year, and about 90.8 billion are lost due to health problems every year, just because of NOx, right? Now, this is understood, and this is actually the reason why there is essentially a chemical plant under modern diesel cars. So they have under the hood, they are running a small chemical plant. And I have to tell you a little how this plant works so that we are set. So you have basically the exhaust of a modern car, and there is the exhaust gas coming from the engine, and out, if you don't do anything, comes this NOx, and this NOx is actually, as we understood, dangerous to your health. Now, there are a few things that actually make it that there is a control loop, basically. There is a kind of reduction chamber where some reduction happens, there is a sensor here which is used for kind of closed loop control. So you can sense how much of this NOx is coming out. And well, then you have to inject something here. It is injected basically there, a certain fluid that reacts with the NOx in order to make it actually harmless. And that is the reaction that is needed for that. So you take a bit of NOx, you take ammonia, and out comes water and nitrogen, right? And these two things are harmless, while NOx is not. Now, this ammonia is supplied in the form of, well, it's called Adblue, or DEF, diesel exhaust fluid. And the short version is basically, at a certain temperature, this reaction takes place, and the sensor here allows the doser to dose the right amount of ammonia so that essentially, if well done, no NOx comes out of the exhaust pipe. So as I say, it's basically a small chemical plant that is below each car that has this SCR, selective catalytic reductor, which is the most efficient technology, and it effectuates closed loop control. I should say that this is for diesel engines. So for standard combustion engines, NOx is not the problem. NOx is a problem, especially for diesel. While diesel are supposed to be superior to the standard fuel, they have this problem that they create NOx. Okay, I will not discuss with you that, of course, electric cars are even better and so forth, but we are actually looking at the diesel problem. And we are doing this because we want to learn. Now, how is it being checked that things go well if a new car comes on the market? By the time this diesel scandal erupted, it was like that. The idea was that you would have a reproducible test for exhaust emissions. For that, you would fix the vehicle on a chassis dynamometer, so it couldn't move to the side and you couldn't turn the steering wheel. And then you would drive a very precisely defined kind of profile so that you get actually reproducible test results. That is the good side of it, right? So if you do this with different cars from different manufacturers, because it's so deterministic what you're supposed to be doing, you can actually afterwards compare one car against the other. That was the idea. Now, and this is how it looks. So you basically, you speed to 50, you speed to 50, you speed to 50, you speed to 50, and then you imitate a bit of motorway. This is in kilometers per hour. You speed to 120. So this is not a German motorway, but it is a motorway, let's say. Yes. Now, well, zooming ahead, let's say, I have a long story what was going on there, but let me just zoom ahead and tell you that, okay, it is started cold at 20 degrees Celsius, which means the car is parked more or less in the garage the day before. And this cycle is done 5 times on the day before. This is the cycle 5 in order to clean the exhaust pipe. Basically, this is also defined. Now, what was found once upon the time in the diesel engines of Volkswagen was these kind of piecewise linear functions that were in the code, and the code was obfuscated. And these piecewise linear functions now have something to do, well, have something to do with the behavior, of course, of the test, right? Now, what do they have to do with each other? Basically, let me just go ahead. Well, in the yellow part, exhaust cleaning is actually turned off, and only in the white part, exhaust cleaning is turned on. Now, if you take this European driving cycle, which is, I mean, this one is over time, and then it's distance, and this is over time and it's speed. So if you build the integral over this, over the distance, basically, right, over time, basically, to then get to the distance one, then this is what you find as the curve, and then you see how it fits into what was hard coded in the control loop, so to speak, right? So essentially, it was catching the behavior that was hard coded and that was deterministic, was basically yeah, well, it was basically caught by the designers, and this was very good German engineering in a sense. The code was provided by Bosch, and Bosch basically said, don't use this in productive code, but Volkswagen decided to do that. And what you see here is actually what has to happen on the day before. If you do this here a number of times, then you end up there. And this is if you go full speed. So you see it's basically designed to use the exhaust cleaning only for things that are obviously the test, the one test that is deterministic. Now, you could now ask, you could now ask, what did others do? And it surfaced that many other companies did things, let's say, in a fishy way, let's say. The engineering was very good, especially for Volkswagen. That's why they were most in trouble. Others did it a bit more indirect. For instance, GM, that at that time was together with Opel, they had a speed limit, they had a temperature window, they had a fuel temperature window. So the fuel in the tank was decisive for the exhaust cleaning, which doesn't make a lot of sense, except that you know that the whole system does happen at 20 degrees. So if your fuel is overnight has gotten a temperature of 20 degrees, then right, I mean, this is basically an indicator for the test. What Porsche did is they were kind of, well, clever. They said, okay, if we are on this chassis dynamometer, there will not be lateral acceleration and there will not be vertical inclination. And so if for a certain duration there is no lateral acceleration, then a Porsche is obviously not used in the way a Porsche should be used. And so they turn off exhaust cleaning. Now, Audi had an interesting, had a few interesting stories. One was if they were running low on this on this AdBlue, they would just stop using the AdBlue. They were not waiting until it would be empty. They would just, when it's getting close to, let's say, the bar, they would just not use it anymore, right? Which basically also means that they don't have to refill the DEF until the car comes to the garage. Okay, now let me go on. FIAs, why do I say do? Here I say did. I say do because as far as I know, they're still doing this. Namely, they turn off after 22 minutes. This is a good idea because the test is only 20 minutes, right? Well, so it is effective. They are, of course, saying, like many others, they are saying that this is because it protects the engine and so forth. But it's, of course, an effective way to pass any test that only lasts 20 minutes. Now, of course, this is fraudulous behavior. But, I mean, who is actually doing the fraud? I mean, there is no attacker, right? It's not that someone has sent you a virus or something, right? The fraud is actually built into the product, and that's what makes it interesting, right? So zooming out, I mean, it is the biggest problem, let's say, that is of this kind. But of course, it is only an instance of a set of problems that we consider interesting to look into. And we call this software doping. So the name is not coined by us, but we think it's quite okay. So it is, right? It's about the illegal use of let's say, substance, here software or a technique, to illegally improve the performance in a way that is not intended by, let's say, society, right? This is here the problem. So, and software doping you find not only in cars, you also find this in printers, where certain cartridges are rejected just because they're not from the brand that it's is actually selling the printer, right? There are a number of interesting stories just around this, with time bombs and all kind of crazy things, right? So this is one example. Another example is, okay, this kind of message that you are not supposed to be using an adapter if you want to charge your Dell laptop that you have bought from a third party. You're supposed to buy it from Dell, right? Now, of course, this is an interesting trade-off now, because it could be because the other adapter is unsafe, right? And it basically maybe blowing up your laptop, right? Or it blows up the airplane or whatever once you have charged your battery with that, right? So it is an interesting question now how to make this, let's say, a formal characterization, right? Here's another one. So after an iPhone update once upon the time, those iPhones that had gone through a non-authorized repair shop beforehand stopped working after an update. This later turned out to be unintentional and it was fixed by another update. But for a while, it looked like this was intentional in order to lock the customer into repair shops that are authorized by Apple. Yes. So these are instances of software doping. And I have now decided to make it a little short. I will give you a characterization of what we think is software doping. A software is doped if the manufacturer has included a hidden functionality in such a way that the resulting behavior intentionally favors a designated party against the interest of society or of the software licensee. Now, if you read this and you think a bit with me, then you will likely realize that this is difficult to formalize, right? The intention is difficult to formalize, right? I mean, but without that, you can try to formalize that. You will find that what is needed is some sort of contract between the software manufacturer and the customer that essentially says what functionality is good functionality and what is not, and in how far a test run is supposed to generalize beyond the deterministic conditions of that very test run, if we think of the car issue. So now what would we expect? Essentially, we would expect that if the input values that are put into the program, so to speak, deviate within a reasonable distance from the standard, the output values will also stay within a reasonable distance from the expectable output produced by the input. And there we have to identify what inputs are to be considered. For instance, lateral acceleration should not be considered at all, for instance, right? So this is what is meant with standard. Now, in mathematics, it looks a bit like this. I don't think it's so important, but you have input distances, you have output distances, you have standard inputs, and you have the values of interest, the dimensions of interest, basically, right? And much of this will have to go into a contract between the, as I say, the customer and the manufacturer, so that you agree essentially to what extent behavior that is specified not only applies to the particularity, but also goes beyond, right? So for instance, the kappa I and the kappa O and so forth, the distance functions and the standard inputs, they have to go into a contract. That is the idea, right? Now, we have been doing a bit of work. Let me probably summarize this. It assumes the contracts with the parameters of interest, the relative inputs, deviations input, and lead to deviations at output. This is what needs to be in the contract. And we have done a bit of work. You can essentially, write this in logic and you find that this is actually a hyper property. So we have encoded this into hyper LTL. You can also reformulate this with Hausdorff distances, and you can make this run over infinite words. This is basically when it becomes a hyper LTL formalizable property for reactive systems. And in our first work, I think this is from 2018 or so, or maybe 17, we did verification. So we assumed we have white box access to the code. And then we basically can code this into, as I say, a hyper LTL property, and we can use model checkers for hyper properties in order to actually verify the absence of doped software. Yes, that was step one. But it's a bit silly because in reality, you don't have white boxes, right? So especially for the automotive context, I mean, the software is no white box. I mean, the diesel scandal, the details of the diesel scandal with Volkswagen only came to the public surface because some hacker actually managed to exploit a 0-day and actually crack the software. And then it was possible to look into this, right? Because of course the software is intellectual property. So it is a black box, right? So cars are notorious black boxes and many other systems. So what we need is black box doping tests. Now the question is, now if we do this with formal models and so forth, can we twist model-based testing in this regard? And and if so, is it possible to catch those who have cheated concretely for the context of diesel emissions, right? So, well, you need a few things. You need this contract, right? You need you need to assume that there's a contract that is offered by an OEM, and you need a car. You need a kind of reference tests, maybe a few of them, with test results for that very car. And for that, you need a consensus. What actually are the parameters of interest? For instance, lateral acceleration is not a parameter of interest. Exhaust temperature could be a parameter of interest, right? And what we did actually, we defined what we think is a reasonable contract. We made it very, very loose. And then we tried whether for the existing cheating technologies that we knew of, do we have a test that can actually show that the cheating was there in this, according to this contract, right? For that, to get there, there are a few issues. Maybe I go quick here. If you have multiple of these orange reference tests and you have, let's say, the distance around, then you may end up in strange situation that, well, here you are within distance to a test, but there you are within distance to another test. And so you need to some actually history-aware constructions in order to exclude inconsistent behavior. This is a bit technical what we did there. And what basically boils down to spelling out hyperproperties as input-output transition systems. And then you can, from this input-output transition system, you can on-the-fly generate tests, namely on-the-fly doping tests that are based on input-output conformance, which is one of the standard notions for input-output transition systems. This is how it looks like. Maybe I don't have to go into all the details here. What I will be doing is I will show you what this actually means. So this is the NEDC, the standard test that at that time had to be done. And here is a test that is, you see it here, it goes to here, it goes to there, it goes to there, it goes to there. So it only differs in the first 200 seconds of the NEDC by very little. And if you drive that, you turn off the exhaust cleaning. So at the end, the exhaust value, the NOx value will be much higher. So this is basically a distinguishing test that breaks the contract, and it's only let's say the kappa I has to be chosen very little. The difference in input has to be chosen very little. This is one example. We did the same actually for all the others. That was actually possible. For Fiat, it's not possible just because they are strictly not violating the test, right? The test is only 20 minutes, and what happens afterwards is not specified. So if you want to catch them, we need more consensus how reference tests are meant to extend beyond the time. They can also not extend forever, because this would mean that a car cannot age at all, right? But some consensus is needed for the time after 20 minutes. And this is an interesting intellectual question, I would say. We were also not able, by the way, to catch BMW. This is because BMW cheated for some cars by simply shipping the wrong software. They just didn't know what software they had to ship with the car, and they shipped the wrong software. So a software that never would have made it to pass the test, even in the original form, let's say. Yes. We also looked with this technology, we looked at a particular car, a Nissan car, for which we didn't know. So for all of this, the problem was known, and it was easy actually for us to resurrect this. For here, we didn't know the problem, and still we were able to show that I mean, we have a test run that essentially shows that this is grossly over exaggerating the exhaust value of NOx for this car. So that was that. Now, slowly we go to runtime monitoring. This is what we then did next, namely the time changed. I mean, the diesel emission scandal is now 5 years in the past, basically, when it all started. This NEDC has been changed by something which is called a World Harmonized Lightweight Traffic Profile, WLTP. It still has the same problems. It is a single deterministic test run, so it's easy to identify. You have to put your car on the chassis dynamometer. It gives you reproducible results, but it's again very easy to cheat. For that, actually, there has been something entirely different that is being rolled out, and it's used nowadays for type approval in Europe. It's called RDE. So what is RDE? RDE stands for real driving emissions. And what it actually does is it checks for emissions on the road. For that, you need a device that measures the amount of exhaust while driving, right? And because this is now in real traffic, it is much harder to identify actually that an RDE is happening. And of course, the results are not reproducible. You can no longer say that this car is better than another car because the traffic situation is just non-deterministic, so to speak, right? And so only a kind of maximum value, a threshold, is determined. Now, how does this look like? Let's go a bit deeper because we're talking about runtime verification. So the procedure basically says, well, drive for some time, between 90 minutes and 120 minutes, and then check a number of conditions. And if it's a valid RDE trip, then look at the NOx limit. That is one number. And if this number is exceeded, then this is a bad car. Otherwise, it's a good car. Yes. So that's how it goes. Now, what is a valid RDE trip? Well, a valid RDE trip consists of an urban phase, where the speed in kilometers per hour is between 0 and 60, a rural between 60 and 90, and a motorway, which is between 90 and 160, right? If it goes above 160 once, then this is not an RDE, for instance, right? So, which is not possible in many countries, but there are some. Now, these things, I mean, each of these segments is at least 16 kilometers long, and they don't have to be like that. First urban, then rural, then motorway. For instance, this is a valid RDE that was driven, and you see red is motorway, purple is rural, and green is basically traffic in town, essentially, right? Urban traffic. This is how such a thing could look like. But you see there are many, many possibilities. And what is taken is the exhaust measurement at the end of the accumulated gas. Now, if you look at the RDE conditions that are specified in a European standard, you find, for instance, that the ratio of urban should be between 29 and 44, of rural between 23 and 43, and so forth. So you see a number of conditions that your speed measurements now have to satisfy. The speed measurements are basically indicated here, right? Then you have distance requirements. You have some other additional constraints. You have temperature constraints. You have altitude constraints. You have duration constraints. And you have driving dynamics, which talks about certain percentiles of the acceleration, right? Relatively complicated things. Now, what actually was presented in an RV paper 2 years ago, or sorry, 3 years ago, was basically how to code this into formal language, right? So these are the regulations. And now how do we check for compliance? So how do we check whether a trip is actually an RDE? That's the only question that we have now. And well, one way of doing this is to code this, I mean, give this to a programmer, and he will code this all into something. Now, what this RV paper 3 years ago suggests instead is to come with a formal specification from which you can generate a monitor that is not hacked, but is, let's say, right, provably correct relative to the specification. And the specification has a closer distance to the original text, right? Now, I think we agree why this is good. If you code it hard, then this is less succinct and also not perspicuous. It's highly error prone, and there's a low level of abstraction. While if you go via a formal specification, it can be succinct and precise. It's perspicuous and intelligible. It's less error prone. You can have a high level of abstraction, and also you can pinpoint certain ambiguities, right? Now, how do we do this? We take RT Lola, which is a real-time monitoring toolkit for cyber physical systems and networks. This is developed by Bernd Finkbinder's group in Saarbrücken at the CISPA Helmholtz Institute. And it is used actually for two different applications of drones. It is developed, and the engineers there are helping in order to get this to be a good and usable language. The idea is, I think, clear. You have a system under observation. You have a specification, what is the intended behavior, and then you have a runtime monitor that goes over the input streams and checks and produces output streams. Yeah, right? This is what's happening there. Now, so it supports processing, evaluation, and aggregation of input data streams. It can generate a monitor from a given specification. The specifications are checked statically for memory requirements, and either then they are directly executed, or you can also compile them onto FPGA. So this is actually what they're doing. They have drones flying that have these RT-Lola monitors on their FPGAs now. We have a slightly different context. So the specifications are basically, you will see a few examples, equations translating input streams into output streams. They are, as I say, I like it a lot, even though I'm not a code developer, I like it a lot. I think it's really good, intuitive to use specification language. So how does it look like? Well, for instance, if you want to know what is the maximum velocity that is driven so far, and these are your velocity values that are sampled every second, right? Then, okay, well, you have some input streams, you have output streams that are functions of the input values, and they can also use some earlier output values. And well, this is then how it looks like. Let me do this by example, right? So you start somewhere, and then at some point you take always the next velocity. I think it's relatively clear what will happen. So you start essentially with 0, and then you build the maximum of 0 and 46. You find it's 46. Okay, next value comes in. You build the maximum. You find it's 51. Next value comes. Okay, nothing changes. You and so forth, right? So you're applying this function over and over whenever a new value comes, right? And this is then how it's going to look like. Now, if instead you have to have the maximum velocity driven during the last 2 hours, well, it gets a bit more nasty, but it's still possible because you can enumerate, basically, if you have 1 measurement per second, you can enumerate all the values, and you can still write the function so that you get the maximum during the last 2 hours. And this is actually what we need, right? So you see now that there is some kind of memory issue here, right? Now, how to get this all done. This is basically from the runtime verification paper 3 years ago. This is all has let's say good complexity, and you can actually do it. Now, how is this with the more interesting parts? Now, maybe I go to the one part that is really interesting, namely, at some point you have to talk about percentiles, right? Now, also here it is still possible to code this in RT-Lola. RT-Lola is based on Lola, and for Lola this was somewhat hacky, but now RT-Lola has support for these kind of things, so you can actually essentially code the whole RDE in a specification, in an RT-Lola specification. Okay, now, yeah, well, as I say, it's cheap with respect to update cost, and it's linear in memory, so this is actually pretty okay. Now, what did we do then? I mean, now we have something that can essentially run in a PC, right? And it can sit in the car. So it can sit in the car, and it can monitor the speed and the other things in order to understand whether you are on an RDE trip. Now, what you need then is you need this kind of calibrated measurement device, which is in the order of $250,000 because it is, I mean, this is super expensive, and it's super good stuff. Now, what we did, actually, we replaced it by some cables and an Arduino board, which you can buy for less than 100. And the idea is basically that somewhere, I mean, the point is these SCRs, they have a NOx sensor, right? And if you manage to find a certain place in your car, namely, usually it's here, it's on the left of the driver's seat, and you plug in a certain plug, and you do a bit of thinking, so to speak, then you can read out what the NOx sensor tells you. And you can also read out the other things that are needed in order to follow, basically to provide the input streams for the RT Lola spec, right? This is how it looks like. And what you can do with this is like this. So for instance, this is an Audi A7, which has a known problem, and it was extremely easy to reproduce the known problem. So we were doing 2 RDE runs. One was with a full tank of DEF, of diesel exhaust fluid or AdBlue, and the other one was with an almost empty urea tank. And the red is the NOx values that were recorded. The limit for RDEs is 168, and you see basically here, this is below the limit, right? So you have to average it, but that works. Here, if you average it, you will be above. And this is actually indeed the problem. So the Audi by now has been taken back to the garage, and this has been replaced, and they have been apologizing and so forth. But so you see, this is possible just because you can access essentially this NOx sensor. Now, this was step 1. Now I mean, basically we have found doping, obvious doping now. Now, now we are doing step 2, which we call runtime verification for the masses. This is a Tucker's paper from this year, basically, where we are presenting this. We now have a journal paper ready, and I'm quoting a bit of that. So what is the difference now? It's no longer that you need a PC somehow, but you let it run in your phone, and you don't plug into this device that is in the front of your car in this interface. You do this via Bluetooth, right? So that is the idea. So what's the point? These cars are equipped with standardized diagnostic interfaces called OBD2, onboard diagnosis. These sensor readings are exposed via the OBD2 port. These modern SCR systems have these NOx sensors, right, where they don't really get you the result that you want. We need this really in mass, but this is parts per million. So you need still to do a bit of calculations, and you have to be lucky that the right other sensor values like mass, airflow rates, and so on are exported. But then you can just buy a Bluetooth adapter, which you can get for $5, so €4, basically, you can get this. And now you understand why we have this funny logo here in the corner, right? So we have branded 100 of them. So if you want, send me an email, I send you one of these adapters. Of course, they not only work in Europe, they're anywhere on this planet. For every car after 2006 or 2007, such a plug is there, unless it's an electric car. It's related to exhaust, so electric cars are not forced to have that one. But for the others, it's standardized, and it's also standardized what is supposed to be happening there. And we just hooked this up. And then, well, what did we need? We needed to make now RT Lola run in the phone, right? I mean, we had to make this run in the phone. And by the way, this is only for Android at the moment. It's not for Apple. And we needed this kind of approximation of the NOx mass because we only got the ppms from the sensor values, right? But this is under control. We know how to do this. So what we have now, we have this app called Lola Drives. And indeed, the engine of RT Lola now runs in the phone. And the RDE specification is separate. So in effect, it's spearhead for future apps for runtime monitoring, right? I mean, basically, you just change the RDE specification, and you can also monitor other things, right? I mean, for instance, if you have a heartbeat sensor, you can monitor that, and so forth. It's all there. The RDE specification is a separate component and can be replaced easily. Yeah, well, and it supports 3 variants of specifications, which are for different configurations of onboard sensors. It depends on what is actually offered by the OBD adapter. So we can compute the value in different ways. And by the way, of course, this is not calibrated at all. It's also a sensor that is under the control of the manufacturer. So the manufacturer could cheat to us by giving us wrong values if we would understand what we were doing, right? So this is not at all binding. It's just an attempt for us to make to the user plausible what's happening with the car. Okay, so all these data are logged and stored. We have a dedicated format for this data that combines the real-time data and other data. We can do a little bit of analysis on the device. There is a data donation option. So we invite the user. So if you go to the Google Play or you go to here and you install the app, then you will be asked whether you want to donate your data. If you do that, we get the data. We don't get the GPS data unless you allow us to also look while you are doing an RDE trip. Then we also collect the GPS. The GPS we only collect when you are doing the RDE test. Otherwise, for that we need it actually. And you can opt out if you like. And the data donations are fully compliant with the GDPR. We have been taking quite some care there. Now, how does it look like? So this is how the app looks like. And you have essentially, you have two modes. You have an RDE mode and you have a monitoring mode. The monitoring mode basically works even if you have a non-diesel car, an arbitrary car. Basically, it just records all it can know about it can get from the OBD about your car. So it looks like this. You have here the engine coolant temperature, the RPM, the speed, intake air, and so forth, right? So you can see quite a number of values, and this is for your information. This is logged, and you can actually access it later. You can donate this to us, then we make statistics. Yes. Now, the other mode is the one which is unique. We are pretty sure that we are the only ones who are offering an app that can do RDE tests. So this is now about that one. It only makes sense if you have a diesel car which exposes the right quantities to us, right? And how does it look like? Ah, yeah, here this is how the page looks in Google Play. Now here is how you are going to use it, right? So the first thing is you find a potential route that you want to drive on the map. This is not entirely easy, so you may need a few tries. And then you, let me click on this, then you see a bit of a video. So you open the app, then you select your adapter, right? And then it says connected at some point, it will say connected here, right? Then you tap on RDE, and then you can specify the distance limit. So there is quite some flexibility, and the quantities depends on each other. So you have to guess somehow a distance to start with. 80 is a good distance. And then you can start it. And what you see then here's the total time, obviously. Here's the total distance. You have been driving all the distance currently in the urban segment. Here is the NOx that so far has been generated per kilometer. You are supposed not to go above this if your car has been brought to the market in 2021. Sorry, not higher than this for 2021, and not above that for earlier for older cars. So there has been a change in the regulation in this year, and this is average, right? So you can get closer if at the end you are not, right? So then it will be a valid RDE test. Currently, it's not. It's undecided whether it is one. If there is a red cross here, then it says basically it is clear this trip can no longer become a valid RDE trip, right? And then you have these different, the urban phase, the rural phase, and the motorway phase. Here are the kilometers, right? This bar is computed and that bar is computed relative to the 83 that you have been given in the beginning, right? And then here it is about the trip dynamics. Well, maybe we go one step further. Oh, now this is, I think, hello. Yeah. So here you see we have now been driving some time. We are still in the urban sector, and the dynamics have moved a bit, right? And essentially, you have to target the dynamics so that it essentially goes above this white bar a little. Right? There are a few guidelines that we are giving you how to do that, but as you see, you can do your own RDE test. It's better if you have a co-pilot that looks at the app while you are actually driving the car. Yeah, this is another. Wait a second. Hello. Yeah, this is another show. Now we have already done quite some urban stuff. Now we are going to the rural phase. Later we will be going to the motorway, and it is still undecided where we stand, right? Let me go to the last sample. This is once it's done. So you have now, okay, you have been driving 88 kilometers, but it says already, okay, if you stop now, this will be a valid RDE trip, okay? And then once you have stopped, it tells you about what has happened. So the total trip duration was like that, the distance was like that, this was the NOx emission. That was on average, and it is good. It is below the value, so the car is a legal car, so to speak, and then it gives you statistics over urban, rural, and so forth. So this is serious stuff, I would say. I am quite impressed by what we have been doing. It was actually quite some work, and there's a bit of background also that I want to tell you about. Namely, there is a data platform behind that is dedicated infrastructure to manage and analyze the recorded diagnostic data. At the core is this data format for car-related diagnostic data. And yeah, essentially, you can have various specifications here. You can try out certain things. I mean, we also use this for testing, but also, of course, in order to look through the data donations that we are receiving. We had a press release out for this one about, I think, 2 weeks ago. And we have been distributing about 50 of these adapters since then to random customers, so to speak, that send us an email. We have another 40, basically, and I'm happy to give you one if you are interested. Now here, this is how then the data platform looks like. Let me show you also one thing more, namely, of course, we need to test the app. Now, testing the app means sitting in the car, driving and connecting it and feeding it with real stuff, right? Which is, of course, a lot of effort. Not surprising, we have built a simulator for that. We decided to build it into a silly smaller car. And there's an Arduino then in there that imitates the behavior of a car from the perspective of the OBD2 interface, right? And so if we're developing the app, basically, then we are testing the app basically in our lab by this car simulator. So that is actually my story. So I have some useful resources in case you are into runtime monitoring and you like the idea. I mean, all the code that we have is open, and you can get that. So the first one is RT-Lola. So this is written in Rust, and Rust uses LLVM as a backend, and this in turn makes it possible for us to compile it for Android devices. And you can get the RT-Lola toolkit at this address here. Then there is an interpreter, but also there's a library that exposes a C-compatible interface, which then in turn can interface with the JVM-based languages such as Kotlin. And why is Kotlin important? Well, the other parts are written in Kotlin. So this is at this link, you can find the RT-Lola interpreter. Now, this then interacts with the Lola Drives app, which itself is written in Kotlin. And this is here, right? So there you basically find the Lola Drive app for Android. We are working on an app for Apple. I should say that this one here runs on Windows, Linux, and so forth, right? It also runs on other devices. We, of course, have been focusing with Lola Drives for the app market, right? That is the specialty. And then for the car data platform and all that, they are also written in Kotlin. You find them here at this link. And we also have Maven artifacts that are there for integration with other projects if you're interested in that. So I invite you to make use of that. What have I actually been telling to you? So I think I'm good in time, I would say. I've been telling you about our research, which of course is on the one hand, the RT-Lola framework, which is this runtime monitoring framework. It's the core of the RDE evaluation, and it gives you provably correct monitors. Then we have been working on software doping, namely the detection of undesired hidden software functionalities. And we are trying to learn more about behavior of cars and the amount of doping by looking at the data donations. Then I think this is quite unique in the sense that the research is accessible to the public, right? So essentially, I would say this is really, really en vogue research, and still it goes out to the public, and we get lots of people that think this is cool and they want to actually help us crowdsourcing data. And well, this Lola Drives app has this unique functionality that it can do affordable RDE tests for many car owners. Now, this will not be a true test because calibration is missing and so forth. I have discussed this with you actually at length, right? So it's not really an RDE test. Now, who did this? Well, I mean, basically, this is the groups of Bernd Finkbeiner at the CISPA and myself at Saarland University. Let me tell you who has done what. So Maximilian is the person who is behind the RT Lola development. Yannick is the one who has done who has really implemented the app. So he is the one who has implemented the app. Maximilian is the one who has formalized the first version of the specification of the RDE, basically. And Sebastian is the one who looks over the shoulder of Yannick, basically, and is also, he's doing the test rides. He does the car data platform and all that. And he is essentially the one who stands, if you want, most for that. But it is collaborative work of a number of people. And there are actually a few people like this person, and there have been earlier versions of the app, and there have been more cables. These are all different cars, by the way, that you are seeing here. Not one car is like the other. We have been doing quite some effort there with a number of people, and I'm happy to thank all of them, especially these people. Thanks a lot for your attention. I'm happy to take questions.
Thank you, Holger. That was a great talk. So
okay,
we can take questions now. So you can either unmute yourself and speak, or you can put your question in chat.
So Holger, thank you. This is very interesting talk. I noted that in one of your last slides, you have a footnote said this is not really equivalent to the legal compliance. So what do you think would be the gap, or to make this work from runtime monitoring to become a future tool, maybe for legal compliance or certification? Do you think what is the gap, and what do we need to do?
So this is a very good question. So actually, if it is about is this driven behavior an RDE, then I would say we are very good, because also the normal RDE equipment will use the OBD adapter for the speed, for the throttle, and these kind of things. So if it is only about is this an RDE, we are good. The problem is we need to measure a certain exhaust, and for that we have very, very bad equipment. We are just trusting the value that is given out by the sensors that could be arbitrary off, and they are also not meant for that. I mean, the unit that is usually put at the back of the car is so expensive because it is highly calibrated. It can absorb the whole volume of more than 1.5 hours of driving, basically, right? So this is completely different from this sensor which sits there and just looks at the particles passing by. So that is actually the problem. But if it's only about formalizing and checking whether a car currently drives an RDE, so whether the inputs provided are an RDE, that I would say is very good. And it's actually also, we call it perspicuous. It is something you can read off the specification, you can look at the text, and you can look at the code, and you can see that we are generating the correct monitor for that. It's just the output that is at the end decisive is not really under our control. This could be cheated. Yeah. You're muted.
Sorry, I have a question. I mean, one of the things that you require here is detecting whether something is an RDE, right? Is it possible for the car to cheat you and make you think it's not an RDE when it's actually an RDE? And is this something you can detect?
So what the car could, of course, do, I mean, I was saying in the beginning that this NEDC and the WLTP, they're extremely easy to detect because they're essentially deterministic up to human driver misbehavior. Here, the RDE has lots more variety. But of course, our specification could, for instance, be used by the car manufacturer to turn off exhaust cleaning whenever it knows this can no longer be an RDE, right? I mean, in a sense, it is an easy twist that if you put this into the car, which is of course possible, then it could be used to show good behavior only if there is some possibility that this is still an RDE, right? This is one way of cheating, let's say. Yeah. Good one. Yeah.
I think there's a question from Borzu.
Hi, Holger, and very nice talk. So you mentioned about verification of hyperproperties, and you don't really have white box in the automotive domain,
Yes.
which is true.
Mm-hmm.
What about gray box? Meaning that you get your executions at runtime and you have a model of your system. It's not completely white box, but it's an abstract model. And then you can do gray box monitoring. Does that make any sense, or no, it has to be completely black box?
So in a sense, we are trying to work on that. So we would like to have a relatively simple or a relatively complicated model of the exhaust behavior of the car, so that we can do plausibility checks more, and we can essentially, right? I mean, basically, this is what you're saying. If we have a model that is, if you want, learned or derived from physics or so, that somehow says how the car must work, then we can essentially, it's only about the decisions that are taken in a discrete way that then make a difference, right? We don't have that yet. We are actually working with Mohamed Moussavi on this to some extent, and also the data donations are hopefully helping us there.
Thank you.
Borzu, do you still have a question? Because your hand is still up, if not.
No, sorry.
Well,
No.
according to the
There you
RT
go.
Lola specification, if your hand is up, you have to ask a question. So,
Never mind.
So this idea of having building kind of a model in a gray box setting is interesting, right? Because one of the things you could also think about using the data that you are gathering through this app is also to kind of build predictive models of what kind of driving makes your emissions worse, or what kind of driving makes your emissions better. So have you given thought to this?
I mean, in a sense, I mean, what would be, of course, nice is you have, let's say, the whole space of possible RDEs, right? And then you do kind of falsification like stuff in order to find what is the one that brings me closest to the critical boundary, basically, right? Now there are some guesses like more trip dynamics is more costly exhaust wise, but it would be very nice to have a model and essentially use the model to guide the real RDE actually then that is being driven. And there's a lot of room for this. We are trying to do this, so we have some work that also tries to use falsification in the test generation, but it depends a bit on that we have nicely looking data, basically that we have a model that we know actually what kind of behavior goes in what direction, and that we can justify that, yeah, from data. Very, very nice question. Yeah.
So we are almost out of time. Do we have any other questions?
So if there should be questions coming up, shoot an email, go to this loladrives.app. There is even the mail where you can directly order your adapter. We are very happy to discuss with you and to get feedback. If not now, then by that means. Yes?
Yeah, thanks, Holger. So I think we are out of time. So let's again thank Holger for a wonderful talk, and I'm quite interested in seeing how this adapter would work. So yeah, hopefully you'll see an email from me at some point.
Cool.
So, yeah.
Thanks a lot.
So, yeah, thanks again, Holger, and yeah. Over to you, Dana, for the next part.